Welcome to the course on game theory in the autumn term 2020 at the University Mannheim. This is the third video of week 8. We continue with examples of extensive games without chance moves and with perfect information. So then the next two examples, Kidnap and Cozy Kidnap, are quite famous. First, I describe the general case, Kidnap. Alice, player A, has kidnapped Bob, player B, and the ransom has been paid. What will she do now? And what will he do if she releases him? And as an example, here is a game tree, what might happen, and what are the utilities of the two players, depending on the result. So first, Alice has to act. She has to decide whether to kill Bob or to release him. So she has these two moves, kill or release. If she uses kill, then the game ends. We arrive at a final play, and the value for her is 1, which is positive but not so high, and the value for him is, of course, 0. Now, if she releases him, we arrive at another play which is not a final play, because now Bob has two options. He can go to police and reveal her identity, and then she will be brought to prison. In that case, the game ends and her utility is 0. She doesn't like to go to prison. His utility is 2. He is happy that she is now in prison. He could also choose the option to remain silent. Then the police wouldn't find her. And here it is better for him than to die, but it's not as good for him than to see her in prison. So this gives value 1 for him. For her, in fact, it would be the best option. She does not really like to kill him, but she also doesn't like to go to prison. She would prefer if she could leave him alive, but would stay free. So for her, it's value 2, the highest value. So, but life is bad. In this situation, the only subgame perfect equilibrium is kill, reveal. So first we have to study the subgame where it's Bob's turn to do something. And he has the two options, reveal or remain silent. And he chooses, of course, the option to reveal because it's value 2 for him compared to value 1 if he remains silent. So, and then, now we go to the smaller game. And now Alice she knows what Bob will do. She is able to do the backward induction. She knows that Bob will reveal her if she releases him. So therefore she has the possibility to kill with value 1 for her or to release him with value 0 for her, so she will kill him. So this is bad for both, especially for Bob, but it's the result of this game. So now we go to the next game. And now we still go look at the associate game in normal form. So here one forgets the order of the events. So Alice has two strategies, kill, release, and Bob has two strategies, reveal or remain silent. But in fact, Alice's action comes before Bob's action. If she kills him, it doesn't matter what he would like to do, what his strategy says, because then he is dead anyway. In that case, the result is 1-0, 1-0. If she releases him, the result depends on Bob's reaction. So if he reveals her, the value is 0-2. If he remains silent, the value is 2-1. And one sees now in this game that kill reveal is the only Nash equilibrium. If we start here with remain silent and kill, then one sees that it's if Bob remains silent, then for Alice it's better to release him. So this is not a Nash equilibrium here. So, but if now we are here, and Alice is going to release Bob, then for Bob it's better to reveal her than to remain silent. So this is also not a Nash equilibrium. So now we are here, release and reveal. Now if Bob is going to reveal if Alice releases him, then it's not good for her to release him, so she has to kill him. So this is also not a Nash equilibrium. Therefore here the only Nash equilibrium is the pair kill-reveal. So now a variation of the game, which happens in reality sometimes. Sometimes it happens that the kidnapped person starts to like a lot the kidnapper. This is some psychological reaction which is probably related to the reasoning which we will see here in the next minute. So here we have the same game tree as before, and the same options for Alice, kill, release, and for Bob, reveal, remain silent. Also Alice's values have not changed. Kill is still value 1, going to prison is value 0, and let him live but stay free is value 2 for her. But now Bob's values have changed. Now, before in the kidnap game, reveal gave him 2 units and remain silent only 1. Now it's opposite. Remain silent gives him 2 units and reveal gives him only 1 unit. This might happen if he has started to like the kidnapper, to love the kidnapper. And then if we look at now at the sub-game, which starts here with the play here, where Bob has to choose between reveal or remain silent, now it's better for him to remain silent. So this is because of the other utility values, now it's a different result, remain silent. So now if we go to the smaller game, then we are here. And now Alice has the option between kill and release, and now in the case release, yeah, the value for her is higher, it's 2 compared to 1 if she kills him. So therefore she will release him. So here the only sub-game perfect equilibrium is that Alice releases Bob and that Bob remains silent. So the associated game in normal form is given again here. Now the values are a little bit different. If Alice kills Bob, still the value is 1010, no matter what he's planning to do, because he's dead anyway. If she releases him and Bob reveals, value is 01. If she releases him and he remains silent, the value is 22. Now the only subgame perfect equilibrium is release, remain silent. So this is a subgame perfect equilibrium, especially it's also a Nash equilibrium. So now if Alice, but we have still the old Nash equilibrium, kill, reveal. This is also a Nash equilibrium here. So kill, remain silent is no Nash equilibrium. If Bob remains silent, for Alice it's better to release him than to kill him. So this is not a Nash equilibrium. And reveal, release is also not a Nash equilibrium. If Bob is going to reveal, if she releases him, then she has to kill him. So, but here we have 2 Nash equilibria, the old one from the other game and the new one. And the new one is now the only subgame perfect equilibrium. So the old Nash equilibrium is no longer a subgame perfect equilibrium, because in the subgame starting at the situation where she has released him, here, the old Nash equilibrium is not a Nash equilibrium anymore. Reveal here, the restriction of the old Nash equilibrium would here be the strategy reveal, but it's not the best option anymore. Now the option remain silent is better. Therefore, the old Nash equilibrium is still a Nash equilibrium here of the associate game in normal form, but it's not the restriction to the subgame is not a Nash equilibrium of the subgame. Therefore, the old Nash equilibrium is no longer a subgame perfect equilibrium. So this really changed because of the values of Bob. So now the moral for Alice and Bob. Alice must be sure that it's better for Bob not to reveal her identity if she releases him, then she does not need to kill him. And I believe that sometimes in reality there is some psychological things happening which are related to this moral. Maybe the kidnapped person is feeling that this is true and then really starts to develop some feelings. But for us important is also that here we have a difference between Nash equilibrium and subgame perfect equilibrium. Here in this cozy kidnap game, we have two Nash equilibria. One is subgame perfect and the other is not. So release remains silent is subgame perfect. Kill reveal is a Nash equilibrium but not subgame perfect, because the induced strategy combination in the subgame after releasing is no longer a Nash equilibrium there. Reveal is not a Nash equilibrium in the subgame where Bob has the choice between reveal and remain silent. So this cozy kidnap shows clearly the difference between just the Nash equilibrium of the associated game and the subgame perfect equilibrium of the associated game. And we see that theorem 514 fits. It really gives us here all the subgame perfect equilibria, which is here the unique one. So, and yeah, somehow this example is important for the development of this notion subgame perfect. We came to this notion from the theorem, from the backward induction, but one should also come to it from some good reasoning. And here you see this reasoning. If you have some extensive game, then it's not enough just to consider the associated game of the full game. We have to consider also the associated games of all the subgames. Because as the game then proceeds, we will come to smaller and smaller subgames, and the strategy combination should always be fine. It's not sufficient that the chosen strategy combination is fine at the beginning, before the game starts. It should be fine also at all intermediate steps. And that means precisely that for all possible subgames, the induced strategy combination should be a Nash equilibrium. So, and then this is exactly the notion which Selten defined as subgame perfect equilibrium. And now we can go back and see, yes, theorem 514 is fine. It gives us exactly these strategy combinations. So, but it's important to motivate these combinations not only by theorem 514 and 514 and backward induction, but also by this reasoning. A strategy combination is good only if it's good for all involved, or for all possible subgames. So this is a strong point for the notion of subgame perfect equilibria of Reinhard Selten. So now we come to the next example. And finally, you will see that there I will start to argue against subgame perfect equilibria. It's some funny change, and Reinhard Selten even did this, and he did it even stronger in the example afterwards, and the warehouse paradox, which comes in example 520. So example 519, it's again two parts, an ultimatum game and a mini ultimatum game, ultimatum mini game. So in the ultimatum game, there is a fixed amount of money which is free for use, and about which Alice and Bob can dispose. So it has to be divided between Alice and Bob, and Alice is allowed to make a proposal how to divide the money. Bob can accept or refuse this proposal. If he accepts it, it is carried out. If he refuses it, Alice and Bob both receive nothing. So here is first, there is a game, there is no game tree here. So the fully rational solution is Alice offers Bob the smallest possible positive amount, and then he accepts. So the smallest possible positive part of the amount of money, and then he accepts. Because if he refuses, he gets nothing. If he accepts, he gets something, even if it's very little. So if Bob is completely rational, he should accept an offer of Alice as unfair as it is, because it is positive compared to nothing. But reality is different, and this has been verified by many, many experiments, even in the case of a high amount of money. So not just some small game money, but high amounts of money. Most of the time, Alice plays fair. Most of the time, her proposal gives herself 50% and Bob 50%. Proposals even like 70% for Alice and 30% for Bob are refused very often. They are refused in more than half of the cases. One might think that 30% is not so bad if it's a high amount of money, but still people have their character and they refuse such an unfair offer. They prefer to get nothing than to accept such an unfair offer. So, this is somehow bad for game theory because it doesn't fit to the notion of a fully rational player. A fully rational player should accept any positive offer. But here we are in this experience, we are in reality. In reality, probably the players do not see the game isolated from the rest of the world. They bring conditionings into the game and also reputations, which they want to keep, and which they are formed by the previous lives. So reputation is that I'm not a person who accepts unfair offers. And this reputation is important because in their future life they want to get a lot of unfair offers. They want to get fair offers. So they should refuse this offer here in order not to get unfair offers later again and again and again. So because of this context then, Bob might refuse the unfair offer of Alice, although it gives him something positive, whereas refusal gives him 0. Now a special game of this ultimatum, or the more restrictive, simplification of this ultimatum game is the following ultimatum minigame. Here the amount of money consists of 4 units, and Alice can choose only between the unfair distribution 3 for herself, 1 for Bob, or the fair distribution 2 for each of them. So and then we get a game tree. So Alice can choose between the 2 possibilities what to offer. The fair offer is 2-2. The unfair offer is 3-1, so 3 for herself and 1 for Bob. In the fair case, Bob has to accept it. So there is no, he should not then start some stupid nonsense. He should just accept it. The game ends there with an acceptation of this fair offer. In the unfair case, Bob can choose between refusal, then both get nothing, 0-0, or accepting this unfair offer, then Alice gets 3 and Bob gets 1. So here the rational, in backward induction, we suppose that both players are rational, fully rational. And then, of course, if you look at this subgame which starts here, Bob here has the choice between refusal, he gets nothing, or to accept this offer, then he gets 1. So here, backward induction clearly says Bob should accept the unfair offer. Then Alice knows this, and then she is in the subgame where she can make a fair offer, 2 for each, or unfair offer, 3 for her, 1 for Bob. And 3 is more than 2, so then she should choose the unfair offer. That's the unique result of the backward induction here. Unfair and yes is unique subgame perfect equilibrium. Now if we look now at the associated game in normal form, then we have here the 4 situations. If she makes an unfair offer, then Bob can say no, value 0-0, or say yes, value 3-1. If she makes a fair offer, what Bob says doesn't matter. Then the rule says he has to accept. So then in both cases, both get 2. So this associated game in normal form is again 2 Nash equilibria. The subgame perfect equilibrium unfair yes, and the Nash equilibrium fair no. So it turns out that fair no is also here a second Nash equilibrium. Nobody can improve his utility by changing his strategy. The other 2 are not Nash equilibria. So if Alice is unfair and Bob has a choice between no and yes, he should choose yes. So here we don't have a Nash equilibrium. Unfair no is not a Nash equilibrium. and if Bob says yes anyway, and Alice has a choice between fair and unfair, she should also go to the unfair option. So this is also not a Nash equilibrium. Fair yes is not a Nash equilibrium. So, but we have here two Nash equilibria, and just as in the game before, one of them is sub-game perfect equilibrium, the other not. So now the reasoning from the last game tells us now that the sub-game perfect equilibrium is the right one. So unfair yes should be played, not fair no. Fair no is not a sub-game perfect equilibrium. That is the philosophy of Reinhard Selten and the value of the notion sub-game perfect equilibrium. Now, one can even extend this game a little bit. One can look also at the mixed extension of this extensive game. And here we see these coefficients. Lambda 1, 1 is the coefficient of the pure strategy S11 in this utility function of player 1, and lambda 2, 1 is the coefficients of S21 for the player 2. So, and yeah, one can put in here the values. So here this is 3, 2, 0, 3, 2, 2, and here it is 2, 2, 0, 2, 1, 2. So we get the values here. And then our reasoning from chapter 3 tells us what are the best reply maps and the graphs of the best reply maps here. So the left picture downstairs here shows the best reply map for player 1. If player 2 chooses gamma 2, 1 smaller than 1/3 here downstairs, then lambda 1, 1 is positive, and player 1 should choose his strategy S11. If the value is between 1/3 and 1, lambda 1 is smaller 0, and player 1 should choose the strategy S12. If it's equal to 1/3, then both strategies are then lambda 1 is 0, and both strategies are equally good, then the best reply set is the set of all possible strategies. And similar for player 2. If player 1 plays something with positive, some combination where gamma 1 is positive, then minus gamma 1 is negative, and player 2 should react with his strategy S22. So only the strategy here. But if player 1 plays his second strategy, if gamma 1 is 0, then lambda 2, 1 is 0, and any combination is the best reply to the strategy of player 1. So these are the two graphs of the two best reply maps for player 1, player 2, and we know that the intersection of them is a set of mixed Nash equilibria. So we have here the picture which we know already from chapter 3, picture where we have two components, one isolated point. It is still the best, the sub-game perfect equilibrium, playing unfair and yes. Alice plays unfair and Bob says yes. But we have also a generalization of the other Nash equilibrium, named Alice plays fair and Bob says no. So here Bob says no with probability between 1/3 and 1. So he has some threat. He threats to play no if Alice makes the unfair offer with probability at least 1/3. So, and for this probability, at least 1/3, the threat to say no with probably at least 1/3, we get a Nash equilibrium with a fair offer of Alice. So the other Nash equilibrium generalizes here to a whole family of mixed Nash equilibria. Okay, so this is what chapter 3 says for the situation. And yeah, we can say, if interpreted as follows: if the probability that Bob says no if Alice chooses the unfair option is at least 1/3, then this is too dangerous for Alice, and then she should choose the fair option. Therefore, we get a mixed Nash equilibrium. The mixed strategy of Bob with some threat, and then the pure strategy of Alice to offer the fair distribution. So and we see then the result for Bob is better than if he expects the unfair thing. So for Bob it's better to threaten credibly to say no than to be fully rational and accept the unfair offer. So here a credible threat is better than to be fully rational. But of course, somehow here I leave the frame which I have put myself. In this game, the players should be fully rational. A threat is not credible. At some point, if Alice makes the unfair offer, we come to the subgame where Bob has to accept or not to accept. And then the only possibility for a fully rational player is to accept. So backward induction should be valid and should go through and predicts the subgame perfect equilibrium, unfair offer, accepting yes. But funnily, the same Reinhard Selten who proposed this notion of subgame perfect equilibrium and who argued that it is better than Nash equilibria, in this situation he takes the opposite position. In this situation he claims that it is better and more realistic anyway, but also better not to follow the own theory from game theory, and not to appreciate the backward induction in the subgame perfect equilibria, but to appreciate the other family of equilibria, credible threat and then fair offer. And he built even an example around this, which comes in the next video, Selten's warehouse paradox, where he repeatedly uses this ultimatum minigame. So I think Reinhard Selten is a person who has some humor, despite all his scientific work. So he had this good notion of subgame perfect equilibria, which really makes sense. But on the other hand, he then introduced this ultimatum minigame and the repetition of it, his warehouse paradox. And there he showed that this notion is not the end of the story, but that one should not be too happy with it. In that case, the subgame perfect equilibrium is not the right choice. The other Nash equilibria are better. And the next video then I will build on this ultimatum minigame and come to this warehouse paradox of Reinhard Selten. Thank you very much.